Friends, welcome to this lecture series, and today we'll be continuing our important topics for your GATE 2027. We have taken many important topics, and in today's highway lecture series, we'll be seeing a topic that is the critical strains in flexible pavement. GATE have asked some theoretical questions based on this, and we will be seeing those theoretical things, and along with that we will also be solving some numericals also. Although GATE has not asked the numericals, but still we will see the numericals also, because they have asked the theory questions. That means they can ask numericals also. Okay. So let us start our this critical strains in flexible pavement. So we are studying flexible pavements. So flexible pavements are what? The bituminous pavements, right, which has bituminous layers. And here we were seeing that a typical flexible pavement is a multi-layer. So the bottommost layer is the subgrade, and then we have the subbase, base, binder and surface. And these layers are normally what? Having bituminous mixes. Subgrade is normally compacted soil, and other are what? Bituminous mixes. So when we are designing this flexible pavement, we are designing as per your IRC 37. This is the code for design of flexible pavements. And when we are designing, the design criteria will consider some failures. Although there are many types of failures occurring in a flexible pavement, we are dealing with two major failures. One is the fatigue cracking and the other one is rutting. The first one is fatigue cracking and the other one is what? Rutting. So, we will see that what is fatigue cracking and what is rutting, and then we will also see the strains which are responsible for this fatigue cracking and rutting, and also we will see what are the concerned equations as per your IRC 37. So, let us start. So, you can see this is a typical image of fatigue cracking. Okay, this is a typical image of what? It's a typical image of fatigue cracking. You can see cracks appearing in the bituminous pavement, and this is fatigue cracking. This is fatigue cracking. Next failure is your rutting failure. You can see there are some depressions happening on the surface. So, this is what? This is rutting. This is rutting. Now, we will see the strains responsible for these two types of failure. We saw two types of failure. The first one is the fatigue cracking. This we saw is the fatigue cracking, and this we saw is the rutting. Now, what are the strains responsible for fatigue cracking? If we see, and just redraw the layers. So, first is subgrade, and then we have the subbase, then we have the base, and then we have the binder and surface. So, this is the base, this is the base layer, this is the base layer. So, the strain responsible for the fatigue cracking is what? It is the strain at the bottom of the base layer, and it is horizontal strain. It is horizontal strain and tensile strain. So, this is a horizontal strain and tensile strain. Therefore, what happens? There are cracks, and the cracks will be found until this base layer, not till the subgrade. If you see here, if you see these cracks, you see these cracks will appear till your base layer. So, I can say this strain, this is a tensile strain. So, epsilon T suppose. So, this is a horizontal, this is a horizontal tensile strain. You can see this is horizontal and tensile in nature. So, horizontal tensile strain, and where you can see this strain, this is at bottom of base layer. This is at bottom of base layer. So, they have asked this question, theoretical question, that which strain? This is horizontal tensile strain and bottom of base layer, and this is responsible for what? For your fatigue cracking. Now coming to this rutting, what happens? Which strain is responsible? Let us see that. So first of all, this is the subgrade, then we have the base, sub-base, then base, and then your binder, and then surface. Now here what happens, you see, here the strain responsible is vertical and it is compressive, and it is at the top of subgrade. It is at top of subgrade. It is compressive strain. Okay, it is compressive strain. It is and vertical. It is on top of subgrade. So what will happen due to this strain? You see, there will be deformations like this. In the due to this strain, there will be deformation in the subgrade, and that deformation will reflect in all other layers. It will reflect in all other layers. Yes, and you can see these depressions. These depressions happening. This is due to this compressive vertical strain at the top of subgrade, and due to which you can see these deformations are found in all the layers till the top. And this is known as rutting. This is known as rutting, and this depth is known as what? Rut depth. This is known as what? The rut depth. So if you are seeing the strain responsible for rutting, what is the strain responsible for rutting? The strain responsible for rutting is this compressive strain. So I can write down here, this is a compressive strain, and it is vertical, right? You can see this is vertical. So I can write down vertical compressive strain. And where you are finding? Where you are finding? Where this strain is there? This strain is there at the top of subgrade. Top of subgrade. So these are the two critical strains and causing two critical failures on which the design of flexible pavement is based in IRC 37. So let me just repeat it and summarize it for you, because they will be asking theoretical questions on this. They will be asking theoretical questions on this. I have already asked in GATE, and they can again ask you. So I can repeat this. So as I told, the design of flexible pavements, we have two failure criteria. One is the fatigue cracking, one is the rutting. Now fatigue cracking is this one, you can see, and rutting is this one. Okay, so there is depressions like in the rutting, and fatigue cracking is cracks. Now for these two types of failure, two types of strains are responsible. What are those strains? You can see for fatigue, I write down here fatigue cracking. You see fatigue cracking. You see here the fatigue cracking is happening due to, first of all, it is horizontal strain, whereas in rutting it is vertical. You can see it is vertical, whereas it is horizontal here. So fatigue cracking is due to horizontal here, horizontal strain, and rutting is due to vertical. Then you see here it is horizontal tensile strain, and here it is vertical compressive strain. So very fundamental difference, that fatigue cracking is caused by horizontal tensile strain, right? Horizontal tensile strain, whereas rutting is caused by vertical compressive strain. Now what is the location of the strain? The location of fatigue cracking strain is bottom of base, and here it is the top of subgrade. So they can ask you this question. So therefore I have summarized here. You see, I have summarized here fatigue cracking versus rutting. Rutting is the permanent deformation which is occurring in the subgrade, which is visible in other layers. So here what is written in the table, I have already explained that. You see, when I am talking about fatigue cracking, the bottom of bituminous layer, or I can say base layer. So the strain is where? Bottom of bituminous layer or base layer. And this rutting is top of subgrade, right? Top of subgrade. So location, first is difference of location. You can see first is the difference of location. You see rutting top of subgrade, and fatigue cracking bottom of the base. So bottom of base and then top of subgrade. Then the strain type, you can see here it is horizontal tensile strain for fatigue cracking and vertical compressive strain for your rutting. So here I have written epsilon C, I can write down epsilon B, whatever. See, you can write down epsilon C also, just a name. Okay. So, you see here, this was horizontal tensile strain and this is vertical compressive strain. So, horizontal tensile strain for fatigue cracking and vertical compressive strain for rutting. And then we have a failure threshold, or I can say permissible value of this fatigue cracking and rutting, which they can ask in the examination. Okay. So, what are those? What are the permissible values? What are the permissible values? See, the permissible values are, for fatigue cracking, it is 20% of total paved area. So, if you have a surface area, so how much fatigue cracking is allowed, or we can say what is considered as failure. When 20% of the area has cracked, then we consider that as failure. And here for rutting, the average permanent rut depth of 20 mm. You can see this was the rut depth. This was the rut depth. Now this rut depth will be different in different locations. So taking an average rut depth. So the failure criteria is how much? 20 mm. Or I can say the permissible rut depth is how much? 20 mm. So this table becomes very important for your GATE examination because they can directly frame so many theoretical questions, or theoretical questions or direct straightforward as the following, or multi-select questions based on this table. Okay, I'll again highlight this. I will again highlight this. You see, first of all, this is fatigue cracking, this is rutting. So fatigue cracking, the location is base of bituminous layer or base of your bottom of bituminous layer or bottom of base layer, and rutting is top of subgrade. I have already shown the diagram. Then fatigue cracking, it is horizontal tensile strain. For rutting, it is vertical compressive strain. Then we are talking about the permissible value, of fatigue cracking and permissible value of the rut depth. So when you are talking about this permissible value, yes, when you are talking about the permissible value, I can say failure criteria or how much is allowed. So for fatigue cracking, we can have a percentage of the area, right? For fatigue cracking, what we can do? We can have a percentage of the total area. So what is the percent total area? The 20% fatigue cracking. So when the failure has in 20% of the area has cracked, so we are considering that is your failure. And here the average rut depth of 20 mm. So this is a very important table for your GATE examination for theoretical. Now let us come to the equations. Now they have never asked these equations. Okay, they have only asked the location and it is horizontal or vertical, all those things they have asked. So they have never asked the location, but we should know the location, sorry, the equations. So let us see the equations. So what are the equations involved in this? We'll solve a short question also on this. Okay, the equation involved in the, we'll solve a short questions also on this. Okay, so for subgrade rutting, this is for rutting, this is for rutting and this is for fatigue cracking. Okay, so based on the reliability level, we have different equations concerning what? This is, you see, NR. This NR is what? This is the number of, standard axle repetitions. This is the number of standard axle load repetition, or I can say design traffic, which might have studied, right, in standard axles, right? Now what is, why this R? Because we are talking about rutting. This is also the number of standard axle repetitions only, but why F? Because it is fatigue cracking. Now you can see that this number of standard axle load repetition is related here to the vertical strain, because the rutting was happening due to vertical strain and vertical compressive strain. Only you see some coefficients are different. Okay, so this is the equation for rutting, and here this is also the equation for fatigue cracking for different reliability level. Here you can see there is a term known as MRM. This is the resilient modulus of the bituminous layer. This MRM is what? It is the resilient modulus of the bituminous layer, and this epsilon T was what? It was the horizontal tensile strain, because the fatigue cracking was happening due to this horizontal tensile strain. Okay. Now this C is the correction factor. And what is the correction factor? You see, when we're conducting this strain experiment and all, that will be in the laboratory, but that will vary differently from the field conditions. So, this is the adjustment factors that will be given to in the question. If they ask a question, that will be given to you. The calculation of adjustment factor is given in IS 37, but that becomes very complicated, so not required for you. Okay. Now, I have framed a small question on this and we'll solve that question also. But before that, this reliability level, you can see based on the reliability level, you can see the equations are slightly different, the coefficients are different. Okay, the coefficient, these coefficients are different. So, how to choose the reliability level? Just remember that for expressways, for national highways, for state highways, for urban roads, we'll take the reliability level, 90%. So, you can say for all the major roads, okay, for all the major roads, we are going with this equation, 90%. So, going with this equation, all the major roads we are going with this equation. Now, for other roads like major district roads, okay, for other roads like major district roads or village roads, okay, village roads, what we will do? If the design traffic is less than equal to 20 MSA, million standard axles, then we'll take the reliability level as 80%. We'll take the reliability level as 80%, and it is more than 20 MSA, then we will take the reliability level as 90%. But if you are designing all these national highways, state highways, urban roads, expressways, it doesn't depend on the traffic. Straightforward, we'll take reliability level as 90%. So, that means we are going to use these two equations. Now, let us solve a question where the number of standard axle repetitions are given to us. Okay, so this number of standard axle repetitions are given to us, and based on that, we will be calculating the strains. They might ask that question. So, we will solve a question on that. Okay, so solve the question. You see here, this is the question. So, a flexible pavement is designed to carry a cumulative traffic of 40 MSA, million standard axles. So, this is that N given. So, this is NR also, this is NF also. So, when I am considering for rutting, it becomes NR. When I am considering for fatigue cracking, it is NF. Okay. And then you can see that the resilient modulus, this resilient modulus in the equations, you see, this resilient modulus, MRM is given to us. This is given as your 3000 MPa, and that correction factor is given 1.12. So, now we have to calculate the two strains. So, this question has not been asked in GATE till now, but they can ask. Okay. So, permissible horizontal tensile strain, and the horizontal tensile strain was occurring where at the bottom of the bituminous layer or base layer, which was responsible for fatigue cracking, and then permissible vertical compressive strain at the top of subgrade. Now, here it is not mentioned which type of road, but you can see the traffic is 40 MSA, which is greater than 20 MSA, right? So, we can clearly go for what? Your 90% reliability. Anyhow, if it is a expressway, national highway, state highway, we can directly go for 90% reliability. And even if it is not given which type of road, the design traffic is more than 20 MSA, so we can go for 90% reliability. So, when I am considering this rutting criteria, I will use this equation, right? I will use this equation. So, this equation I will use, and based on that I can find out this vertical strain, and they might ask you this question. So, let us find out this let us first find out for this vertical strain. So, when I am solving for vertical strain. First, let me solve the second question. So, the equation is NR is equal, the equation is NR is equal to, what was the equation? It is, you see, 1.41 10 to the power minus 8, 1.41 into 10 to the power minus 8, then 1 by vertical strain to the power 4.5337. This is the equation, you see. Yeah, this is the equation, okay. This is the equation. Now see, this number of repetitions is given, standard repetition is given 40 MSA. What is MSA? Million standard accels. It is what? Million standard accels. So million standard accels means what? But I need in standard accels, you see. This equation is standard accels repetitions, but it is given what? Million standard accels. So this becomes what? 40 into 10 to the power 6 standard accels. So here this number of repetitions we should not take in millions and accels, will take in what? Standard accels, okay. Now this is the equation. Now you see 40 into 10 to the power 6 becomes equal to your 1.41 into 10 to the power minus 8, then 1 by vertical strain to the power 4.5337. Now we just rearrange this equation. We just rearrange this. This becomes vertical strain to the power 4.5337. This will become equal to, I just do some rearrangement. So 1 point, this will become 1.41 10 to the power minus 8. And I'll bring this 40 down. So this will become divided by 40 into 10 to the power 6. This equation will change to, you see, 1.41 divided by 40. So this will become, you see, 3.525 into 10 to the power is minus 8 minus 14, 10 to the power minus 16. Okay, this rearranges 1.41 into 10 to the power minus 8 divided by 40, further divided 10 to the power 6. I am getting this value. Okay. So now I can find out this vertical strain, right? So this vertical strain will be equal to this value 3.525 into 10 to the power minus 16, and then this was to the power 4 point. So I'll take a power of, I'll just write down. This becomes equal to 3.525 into 10 to the power minus 16 to the power 1 by 4.5337. So if you write down, we find out this value to the power 1 divided by 4.5337. I am getting a value of, you see, 390.45 into 10 to the power minus 6. This is the strain I am getting, is the vertical strain I am getting. Now you see, this is micro, right? You see 10 to the power minus 6 is what? Micro. This much micro. Micro is given the symbol what? Mu. So I can write down this strain as 390.45 micro. Okay, micro strain. Okay, so I can write down this strain in these terms. So this is the vertical strain which was responsible for the rutting if the road repetitions was this. So based on this equation we solved, and this might be asked in the examination. But this was for the rutting. Yes, see, this vertical strain is responsible for what? Rutting. Now they can also ask you for what? The fatigue cracking, which was the first question. Let us solve for fatigue cracking. So fatigue cracking equation for 90% reliability was how much? It was, the equation was this one, 0.5161 into C 10 to the power minus 4, 0.5161. So NF is equal to 0.5161 into C 10 to the power minus 4. Then it was your 1 by tensile strain to the power 3.89. You see this equation, 3.89. Then 1 by your resilient modulus of the bituminous layer to the power 0.89. 854. So 1 by your resilient modulus of the bituminous layer to the power 0.854. Now these values are given, you see, this is the number of road repetitions, this is same, you see this 40 MSA, so this is also 40 MSA. So 40 10 to the power 6 is equal to 0.5161. C was given how much? What is the value of C? It was given 1.12, the correction factor 1.12 given the question, 10 to the power minus 4. Then 1 by your tensile strain to the power 3.89. Then you see this resilient modulus was given as 3000. So 1 by 3000 to the power 0.854. So if you solve this question, just rearrange the things. So this tensile strain to the power 3.89 will get how much? Do the calculations. This is 0.5161 into 1.12 into 10 to the power minus 4. Then I'll divide by 3000 to the power 0.854. Then further divide by this value 40 10 to the power 6. So I'm getting this value as 1.55 into 10 to the power minus 15. If I want to find out this strain, what I can do? I'll just take this to the power 3.89. Let me check this answer. This to the power 1 divided by 3.89. I'm getting a value of C 155.92 into 10 to the power minus 6, which is equal to how much? Almost 156 micro. Yes, almost what? 156 micro. So this is, I'm getting 390 micro, 390.5 micro. Yes, and this I am getting how much? Your 156 micro. I'll just recheck these calculations and the equation. The equation was 0.5161 and C was given to us as your 1.12, yes, and this was given to us as 3000 MPa. So I use this equation and this is 0.854, 3.89. So just recheck the calculations. So it is 0.5161 into 1.12 into 10 to the power minus 4, then further divide by 3000 to the power 0.854, further divide by 40, further divide by 10 to the power 6. So whatever I am getting, I am taking a value of 1 divided by 3.89. Yeah, I am getting almost this value. So in this way, I got the both strains. They can ask the strain calculation, and till now they have just asked the theoretical question. They can ask the strain calculation. So you should be knowing this. So by using this equation, we find out the strain responsible for your fatigue cracking, which is coming as per the data given 156 micro, and here for the rutting we are getting 390.45 micro. Now this is the vertical strain, vertical compressive strain, and this is the horizontal tensile strain. This is the horizontal tensile strain. Very good, very nice. Now in this question you see this resilient modulus of bituminous layer was given. If it is not given, then we have an equation for that. We have an equation for finding the modulus, resilient modulus of the bituminous layer. Now this is not asked in GATE till now, but they might ask you. So if the CBR is less than 5%, then we will do 10 into simply CBR. And if the CBR is more than 5%, we will use 17.6 into CBR to the power 0.64. Okay, very easy equation. So for example, here I will just give an example. Suppose CBR we have 4%. CBR we have suppose 4%. In that case, what will happen to the resilient modulus? This will become simply 10 into CBR because less than 5%. So 10 into CBR means 10 into 4, which will be how much? 40 MPa. Simply what you see, it is 40 in megapascal. You can see it is simply 40 MPa, right? Very simple equation. Now, if suppose the CBR was 6%, the CBR was 6%. In this case, what will happen? You see, this equation will change to MR is equal to 17.6 into your CBR is 6 to the power 0.64. So how much I will get? 6 to the power 0.64 into 17.6. I am getting somewhere around, you see, 55.4 MPa. I'll just recheck this value, 6 to the power 0.64, okay, into 17.6. So if we have the CBR, from the CBR we can find out what? The resilient modulus. This is the equation given in IRC 37. They have not asked a question on this till now, but if they ask you, then we can easily solve. Okay. So if they ask you this question, we can easily solve. Okay. Let me just recheck these calculations. Yeah, correct. Okay. So this was the short video on your different strains. Okay. So we saw different strains. Now the numericals they have never asked in GATE till now. So you can skip the numericals. I have just given them additional. Okay. I have just given them additional so that if they ask, then you should be knowing that. But the theoretical part is very important. The fatigue cracking is due to the horizontal tensile strain and the rutting is due to vertical compressive strain. Okay, comprehensive. So this is the rutting. Rutting was due to vertical compressive strain and fatigue cracking was due to your horizontal tensile strain. And I discuss this in details. So we'll continue our lecture series in the next class also. So we are covering many important topics. So this is an important topic, the theoretical part at least. So in this topic, if you are not covering everything, at least you should cover this table, right? This table which I have told, this theoretical table. Already GATE has asked 3 times. They have asked 2 theoretical questions based on this. So they can again ask you. Okay, they can again ask you. Okay. Thank you very much. Thank you.